Friends, in the last session, we discussed clearly the possibilities for understanding the structural hazard followed by the data hazard. Structural hazard is something that comes because of the hardware insufficiency, and I explained you with an example of how do we access the memory when there is a requirement to access it from two different stages or two different instructions at the same time, and we understood that it is an insufficient memory over there and we cannot access it. And in the last class, we understood clearly what exactly is the hazard which is related to data. Whenever you have a problem which is prohibiting you or which is restricting you to move to the next level, we can call it a hazard. And here in this type of data hazard, whenever you do not have the data for the next step to proceed, I have three instructions. The second instruction cannot run without the result from the first instruction. The third instruction cannot run without the result from the second instruction. If you have the sequence like this without having the result from the first instruction, I cannot move, sir. That is the problem. If you face, I could conclude it as a hazard called as data hazard. And how do we avoid that hazard? We can avoid that hazards using bubbles, and I taught you exactly to use the bubbles and to stall it. And the most importantly, the rearranging of instructions also at times prevents you the hazards, and it can get you a better flow. In the sense, when you have always the load word and the add combination, you will end up with hazards, and we can avoid that hazards by rearranging it properly. That's what we have seen in the previous session. I hope there are no questions over there in that particular topic. If you have questions, we may probably discuss that in the second half of the session where I can open it for discussion. Now we will go ahead and understand the next hazard called as the control hazard, which is extremely important, and this is something that you will see regularly in your daily day-to-day life. We must have undergone one of the situations at least, and you can relate it nicely with whatever I'm going to tell you right now. So I hope you guys will understand it clearly. Well, let's take a scenario. Whenever there is a decision making comes in picture, whenever you have to wait for a decision to be made, and if you have to wait for that, that hazard can be related to, that delay can be related to the control hazard. Let's take a simple example. I'm going to take the cloth washing as an example again. Let's understand that you are a person who are collecting the cloths in a bulky fashion for all the school children to actually wash it. I mean, you are going to wash the school children's cloth. But what you need to do is you need to make sure that you are getting the correct quantity of the detergent as well as the sanitizer liquid. If you have a stronger combination of the detergent and sanitizer, it could as well damage the cloths. And if you have a weaker combination, it may not clean the cloths as you want. So now the point is, you've got hundreds of clothes available there. For example, you've got 150 clothes available there which are to be washed. You cannot test your combination of the sanitizer plus the detergent quality on everything. So what do? You take one set of the cloth, one set among the available cloths, and you apply your sanitizer plus the detergent formula for it. You see if it is successful, if it is cleaning it properly, and if it is not damaging the cloths. Remember, the combination that you are selecting should not damage the cloths as well. It should not trouble the cloths in any other angle, and it should also clean the cloths. So our task is to clean it but not to tear it off. So we need to understand those two aspects of it, and we are to test it properly by having one set of cloths taken in hand, and we will clean it. We will have to wait until we see the result. For example, it takes about 20 minutes or 30 minutes or an hour for me to wash it. Now what will happen? I need to wait until the cloths really get dry and it should be clean. I need to see if they are all okay, and the amount of time that I'm waiting to see if I get the good results as I expect is a delay, and that delay is a hazard. Very simple. The amount of time that you got to waste ideally waiting for checking if things are right is called the delay, and that delay is a waste, and that waste is a hazard. So how do you handle this hazard, sir? That's the question. I hope everybody can understand the point. I have got hundreds of potatoes to be boiled. I want to know which is the exact boiling temperature of all potatoes, because all of them may go smashed totally if they are over boiled. So I pick up one potato, I boil it, I see if the temperature is all okay. I need to wait until I get the results for this one potato, and only then I can boil rest of the potatoes. So the time that I have to spend towards literally waiting to understand if my combination, if my formula, if my selection is right is called the control hazard. This hazard can be avoided, but again we need to believe on a little bit of luck factor here, and we need to have some sort of okay guts. I decide this way, I'm going to go. Nobody can stop me. I wish I'm going to go right. Kind of attitude, chalta hai attitude will be working out here, and that's what I'm going to show you right now. Till now, can you all understand what I'm conveying about? I'm talking about a hazard which is caused because of delay, which is caused because of the time that you spend in deciding if your formula is all right. Do you understand the point? So if you see that closely, sir, where do we relate it, sir, in computer architecture? Right, we need to think about it, and I'm going to take up a simple example. Right, now what do we do? Very simple. I'm going to take up an example of BEQ and BNE. What is BEQ? BEQ is nothing but branch if equal, and BNE is nothing but branch if not equal. We have seen that very clearly, and I have explained you clearly the methods and the constructs that are behind the BEQ and BNE things. Now, the branching to be taken is a decision. I need to either branch if equal, or I may have to branch if not equal. To go there or not is to be decided. To branch or not is to be decided. That's the point. To branch or not is the decision that we need to take, but the decision is not obvious because you need to do some computation, maybe comparing, maybe waiting for a result. You need to do something to understand if the situation demands you to branch. Do you understand this point? I am going to branch. I'm going to branch if there is equality. I'm going to branch if there is no equality. But anyways, I'll have to do a smaller computation there at least to understand if we have to go there or not. And in case I'll have to branch, I will have to take a different path. In case I'm not branching, I'll have to take a different path. So here, the time that I'll have to spend in understanding, do I have to take a branch is the major problem. I need to understand if the branching is to be really taken, and the computation that is involved in understanding if the branching has to be taken is the core challenge that we are talking about. Now, the pipelining is not powered with the knowledge of if branching is obvious or not, it is going to be taken. You must understand the point. The understanding is very important. I am just having a normal flow. I'm going to add 3 instructions. The pipeline is all safer. There is no problem. I have 3 items in my buffet. I have the first item chapati, the second item the paneer, the third item the vegetable fried rice, and it's all clear for me, and I go with it. I have the chapati, I do not have the intermediate item, and I have the third item now. Now I need to wait to see what the second item is based on what I should take the third. So the point is simple. If you do not know where to go next because you do not have what you have in hand is called hazard. And here in this case, I need to understand if there is equality. If I have no equality there, if I have to branch there is the point. If there is the intermediate item which is going to be good for me, I will take it up and I will go smoothly. If not good for it, I need to go for a dessert to fill my stomach. So I need to either branch or I need to not go for branching. So that is the decision that we are taking, and the pipelining, the entire process of the pipelining is not aware of if we are going to branch or not in advance. So this is a hazard. Now we understand the point, right? Why do we call it a hazard? We call it a hazard because we do not know what to do next. We do not know if we are going to branch or not. We do not know where to go next. Is it a very stable and a systematic stuff that will always branch? Not necessarily. Is it always not going to branch? Not necessarily. So we are in a confusion, and this state is called a non-obvious state where we end up with confusion and we end up waiting. We end up waiting for the processing to be completed, and that's what is called a control hazard. Right. Sir, what is the solution, sir? You spoke about it nicely. I'm okay. I understand it. So, what is the solution? One obvious solution is please wait until the outcome is available. Sir, I need to wait, sir. Do we have to definitely wait? Is there no other go? There is another go available, but I'm telling you, please wait. Wait, you get a definite result, jump for it. You know that it is going to be paneer, so wait for it, and you be very sure that it is going to be there. You have definite time to wait. You wait there, take the paneer and leave, and that's the most obvious option. When there is a branch, wait until the outcome is available. It will then give you the knowledge for the pipeline, which instruction has to be fetched next, how the execution has to go next. All these will be given at a very clear point of view once you give this knowledge. This is the obvious option. Sir, this is very traditional, sir. What is the problem, sir? Yeah, this is very traditional, but that's the way you can do. Now, are we straightforward in doing this, sir? No, we may have to go ahead with additional hardware which can test the equality. Yes, we do it. How do we do it, sir? When you go ahead with branch if equal, we are going for a comparison option. we compare two registers content through subtraction, and then we do the equality test there, and we understand if they are equal or not, and we jump. So this is not done straightforward. There is some hardware involvement over there. So there is some additional hardware involvement over there, which are to be definitely included in the process of you analyzing how exactly the hazard works. So remember, jumping after getting a solution is also not straightforward. It involves some additional hardware cost. Okay, the first point is, sir, I will wait, I will take up the result, I will then analyze, and I will decide to jump or not. That is it. I will wait if they get paneer. If they are not getting the paneer item, I will then decide where to go, whether to go to the dessert or continue to the next item in the same buffet item. That's the answer. Second item, sir, I will be a little bold. I am going to take a decision. I am going to be bold. I am not going to wait for anybody. Yes, that's also possible. How is it going to be possible, sir? Very simple. I take one set of cloth, I start washing it. I understand in few seconds that my combination is going to work out. I'm having a hope. I'm having a thought process and a belief strongly on my selection of the sanitizer and the detergent. So what I decide is, let me not wait. I'm sure of my combination. Let me go ahead and wash all the cloths. I am sure of my combination that it is not going to damage my rest of the cloths, which means I am very particular about what I have done. I am very sure about what I have done. I am very confident about what the result would be. In that case, I am going to go ahead with washing rest of the cloths also, thereby you not waiting for the results to come, thereby not wasting time. The control hazard is totally averted. The obvious option is to wait. The second risky option is to decide and jump. So in that case, you need not wait. But if your luck is there, if your decision is successful, you would have saved a lot of time. But in case it backfires, what will you do, sir? If you start seeing that suddenly the color of the cloths are getting faded and you see that there is a change in the cloth quality, what will you do? You have started washing every set of cloths there. You have started washing hundreds of cloths there. Now what will you do? You will have to immediately pick up all those things and immediately rewash it. Make sure that you can rescue that. So it's the option that you have in hand as a remedial measure. You take it up, put it up in water again, and then start washing it one by one. Find out the right combo and then do it. So the point is simple. The first case, you wait, get the result and go ahead. The second case, don't wait, assume and go ahead. If you are lucky, your jumping would be proper, you would have saved time. If you are unlucky, come back. That's it. So I'll tell you a simple example for this. Till now, I hope I am understandable. I'll tell you a simple example for this. You are asked by your father to buy, say, a biscuit packet. He told you that you need to buy a Britannia Good Day biscuit packet and he asked you to go. He did not tell you that which shop from you should get the biscuit. So he says that you go on the way, I will call you. So what you are doing, there are two shops available. One is in the left and one is in the right. You can either decide to wait when there is a diversion available, for when there is a path available. When you find both the paths to be taken, you will wait there. When the decision has to be taken, you will have to wait there. That's one choice. You are a kid who are very confident about your decision, so you believe that your father will tell you to only go and buy it in the left hand shop. So you start walking towards the left hand shop and your father calls you and your father tells you, son, go and get it in the left hand shop. By then you would have reached the shop and you buy it and come back. So you saved a lot of time there, not waiting for your father's input as in which shop do you want to buy it. So you have saved a lot of time. But what happened, unfortunately, your father has changed up his mind and he is requesting you, beta, please go ahead and buy it in the right hand shop. Now what have you done? You have walked almost 50% of the distance towards reaching the shop and you will have to come back all the way, and that's the penalty that you are paying. The time that you spent in walking and coming back matters a lot, and there is where the risk factor is involved. When you want to predict and take a risk that I'm going to do this, that's okay, I will face the fine, face the penalty if things go wrong. That's okay, you will have to do it. But otherwise, you will have to wait, get the decision done, and then you go for it. So there are only two options available, and I explained you both the options. If everything is correct, if the prediction is all right, it won't affect you at all. In fact, you are going to save the time and it's going to be a favorable prediction. When the luck does not favor, when the things go different, redo everything. That's going to take a lot of time. But how do we do it in terms of computer, sir? You said it. We are going for buying biscuits. We are going to wash clothes. All those examples are fine, sir. But Computers, do they do prediction? Yes, we can let it do that as well. And what is it called as, sir? It is called as the branch prediction, and that's totally related to control hazard. Simple. Whenever the branch requests are hand coming, you predict it and you take the branch or you ignore it, right? You can always predict that it is all taken, or you can always predict that it is all untaken. So branch untaken is an option, branch taken is an option, and based on the results, you may have to penalize yourself by in terms of spending time to recover. That's it. If everything is right, pipelining would produce would proceed at a very high speed, and it's going to be very easy for you. If the branching is taken, in that case, if the branching is taken or not taken, in that case you will have to come back. So stalling will be unavoidable. So this kind of approach is called as branch prediction. To conclude it this way, a scheme of resolving a branch hazard that assumes the given outcome for the branch and proceeds from that assumption rather than waiting to ascertain the actual outcome is called branch prediction. It's a very important terminology, and it's a very important concept. So till now we have seen three types of hazards. The first hazard is called the structural hazard, which is related to the hardware. The second hazard is called as the control hazard, I mean the data hazard, which is related to the outcome of the previous stage. The third hazard that we have seen is called as the control hazard, which is absolutely dependent on the branching. Now, do you have any question? Right. So it's time for us to go to the next level, where we are going to get back to the data path. Sir, you will not leave that, sir. Yes, I'm not going to leave you with the data path. At that level, we are going to enhance that learning, and we are going to learn more for the data path side. The data path and pipelining is going to be the next topic, and we need at least 4 hours for us to completely understand this. Let me go slow so that the learning can be 100% complete. Now, sir, how are we going to learn it, sir? I am going to take the versatile data path that I have taught you a little while ago, and we are presenting the same thing here. Now, when you talk about pipelining, I am talking only about the 5-stage pipelining, and the first stage is called instruction fetch, the second stage is instruction decode, the third stage is execution, the fourth stage is memory access, the fifth is write back. And where are they going to happen, sir? I'm going to visualize it right now in front of you in terms of putting a line where this part is called as the instruction fetch cycle, and the next part, I'll take a laser pointer. So this part is called as the instruction fetch, this part is called as the instruction decode or register read, and this cycle is called as the execution stage, and this is where the memory access happens, and this is where the write back happens. Do you visualize it clearly? Now understand, all these go from left to right. Remember, all these go from left to right in the sequence. There are times where you may have to come back, but mostly if you remember, it is going to be traditionally from left to right that you are navigating. Remember this point. Now please remember, wherever you are going to go right now from here on, we are going to take the same picture as reference, and I'm going to slightly complicate it in between so as to make the understanding better, and I'm going to include couple of items here in, but it's easy. So just follow this. The stages are to be remembered. The intersection here, you can see that the line that I have inserted here should be properly done, and I have got 4 lines to get you 5 stages highlighted. Now, please remember, you do not fold the cloths and then you wash it. You first wash the cloths and then you fold it. So same is the case. Excuse me. I'm going to fetch the instruction, process it, and then I'm going to write back, and I'm not going to do it in the reverse way. But now understand, is it going to be left to right every time, sir? No. There are cases where we may have to think about having the right to left also. They are, the first scenario is going to be, you are going to write back the result into the register for an add instruction. I have to come ahead this way and I'll have to write it back. So this is a right to left. This is a right to left. Now the program counter update also happens on the instruction if it is being a branch. When it is a branch, we have a change in the flow. So it is not always left to right, and there are cases where we have to go with right to left also. But remember, there are certain things that we need to understand clearly. the data flow from left to right is pretty normal and there is no influencing, no change will happen in the entire flow. But the right to left is going to make you some influence in terms of updating the program counter. I could probably go to a different branch. I could probably go to a different address. So there will be impact based on the instruction that we are handling, based on the action that we are taking up when it comes to right to left. Now remember it, pipelining is all about execution of different instructions during the same time. I am not executing, see, they all are to be seen as different execution, different instructions only. You can see that this is one instruction, this is one instruction, this one instruction, but they are all going to be executed in parallel, and that's how pipelining has to be seen. And remember, each instruction should be seen as if they have its own data path. This is a separate data path, this is a separate data path. That is how you should visualize it. When you are writing in the paper or when you are discussing in the interview, the things are different. But in this case, you will obviously have to understand that pipelining is all about executing parallel instructions. Each instruction is supposed to have its own data path, and that's what we are talking about right now. And pipelining is not going to be single instruction being executed one after. It's not that one after another, it's going to be parallel. So that parallel execution should be remembered. With this, I am stopping for the day. I am not going to bug you more than this. Tomorrow, we will understand the importance of this component where we are going to include registers in between. The one that I have highlighted here, if slash id, id slash ex, ex slash mem, mem slash wb, all these are called the registers, and tomorrow we are going to learn all these. Sir, why do we need registers, sir? I'll just tell you a simple point. Remember that tomorrow we'll have a recap again to connect you better. Sir, I am washing clothes in the washing machine. I'll have to put it up now in the dryer. So, do you lift it in hand and put everything over your hand? No, you will not do that. So, what do? You take a bucket in between, keep the items in the bucket, and then throw the items back into the next stage. So, that bucket is the register to hold the intermediary results. So, every stage needs a register, and that register naming convention is very important. We are going to see all of them one by one. So, what is a register? A register is something which can hold the data, and we are going to hold the results of each stage of instruction using that register. As of now, I am closing with this. Tomorrow, we will go ahead and understand how exactly these registers are used, how are they named. All these will be clearly clarified, and we will have a clear-cut discussion. Right? All of you?